In my talks, I presented a new interpretation of quantum mechanics. Today, I will review briefly that interpretation, and then I will show that using that interpretation, we can actually resolve what is considered to be the big mystery of quantum mechanics. You know that Feynman, in his book, wrote that there is one big mystery of quantum mechanics, which is connected with the two-slit experiment. And he said, don't try to ever think about how to resolve this mystery, because you will fall into a big hole and you will never get out of it. So I will show today that using the new interpretation that I proposed, there is a very nice solution to this mystery, and I'm very sorry that Feynman is not alive, that I could show him how we can resolve this mystery. So let me first review the main ingredient of this new interpretation. We start by the issue of what happened in a measurement, and I believe that in a measurement we get just one outcome, so that's sometimes called the collapse, but I look at this collapse in a new way. Instead of the collapse only being relevant for the future, but it's also relevant for the past. And I can explain this new idea in the following way. Suppose we have a particle, electron say, in the ground state of harmonic oscillator. So in one dimension, we know that the wave function looks like that. Now we come and make a measurement, and we find the particle in some location here. The question is now, what can we say about the future, and what can we say about the past? About the future, everybody will agree that we know that from now on the particle will propagate according to the dynamics of the harmonic oscillator, starting from here. But what about the past? We have two options to speak about the past. One option is to say, up to that instant, the particle was still in the ground state. And only from then on, it starts to be localized here. But that is a very strange idea, because if we say that up to this instant, a little bit before, the particle was still described by the same wave function as before, that means that just before, there was a probability to find the charge any place. Then, immediately later, we find the charge here. So what happened? The charge is a charge just a minute before could have been here. It must have come very quickly to this location, and that will cause a big current and all kind of magnetic and electric fields around, and we never observed that. So the only meaningful physical way to think about it is to say that really, if we find a particle here, we can know for sure that an instant before that, the particle must have been here. Otherwise, it doesn't make sense. You have a question?
Yeah, I'm opposed towards the only.
Sorry?
I'm opposed that you say the only logical way. Because if you say that it was found everywhere, then your problem will disappear.
Okay, you suggest...
I don't like it, but...
Okay, let me answer that. What let's suggest, and people that believe in the many world may think so, to say that indeed just before that the particle was everywhere, and when we do the measurement, in the many world we could have found the particle any place after that, any place here, but it will be in different branches of the universe. But I ask now, when I am in one of these branches, suppose I'm the branch where I saw this, in this branch, do I say that also before the particle was spread everywhere? Simply I did not know about it, but that means that in this single branch I have a problem with conservation law. And only when I think about all the branches together, I have no problem. So I refuse to believe that conservation of charge and energy has to do with what happens in all the branches, and I can't consider it in individual branch. I believe that in the individual branch that I find myself later, I can go back and say the conservation law must have applied for this individual branch. Otherwise, all our experiments are always done in a given branch, and we see conservation law in this individual branch. That is the issue. But we can discuss this forever, again and again later. But this is my point. So, the first then new ingredient of this interpretation I propose is that when we do make a measurement, it tells us not only information about the future, but also information about the past. And that leads us to the idea that a particle at any time is described by two vectors, a het and a bra. So if we consider the situation at a given time, I'm saying that any quantum system at this time, when we made the measurement and found the state psi1, at that same time we created also another state which is described by a bra, psi2 prime, and that bra, when we propagate it in time to the second boundary condition, will end up in the state psi2. So we have then a new description of any quantum system at a given time by two vectors, a het and a bra. The het is the state that we found in our measurement. The bra is a state that also propagates the usual way, and it propagates in such a way that it will end up in the state psi2 at the end. And we use these two vectors to discuss a new kind of reality. And this reality can be tested only when we do measurements that are weak enough so that the measurement doesn't disturb any of them. You know, if you have only one vector, you can do a strong measurement that will check this vector again. But when you have two different vectors, and you say that is what describes the physics, then there is no strong experiment that we can do that will not disturb at least one of them. So we must do a new kind of measurement that I call a weak measurement that gives us very little information, but when we collect many, many situations and we do measurement in the middle on each one of them, and then we collect the result of this weak measurement only for this subset that we found the final vector psi2, then we find indeed that there is this new weak reality, and this weak reality is described by a new kind of quantity, new kind of physical entity, property, which is called the weak value. So if we have we have this initial final condition, a time in between. We made some measurement of an observable A. We made a weak measurement, then the value that we find in this new weak measurement is what I call the weak value. It is psi1 and psi2 prime divided by psi2 prime psi1. And psi2 prime is the thing that will evolve to the second boundary condition. This is a new physical property that we can check by weak measurement, and it has very interesting new features, this property. And I've shown to you some interesting properties of this new thing. For example, I've shown that if we look at projection operators on a given location, which we can measure, because we can measure only by local interaction, then sum of projection operators can be negative. And then I showed that the interpretation of this is to have a particle, if we started with electron, and make a weak measurement of some projection operator in some place for this electron, and we found that weak value of the projection operator is a negative value. Then I showed that the best way to interpret it is to say that we found in this location a new kind of particle. It's a particle that has the opposite charge of the electron. It's not a positron, because a positron will have positive mass, but this new kind of particle has the opposite charge of the electron, but it has also a negative mass. And we can check this situation, as I shown in the example of the three boxes. I say, suppose at time t1, I prepare the electron in three different locations, three different boxes, and it was initially in superposition of box number 1 plus box number 2 plus box number 3 divided by square root of 3. This was the initial state. We can certainly prepare such a state by sending the electron with a thing that will reflect it to three different directions. We close the boxes. You see the electron is not outside, so we know that we prepared the electron in a superposition of three locations with equal probabilities. That is the situation at time t1. At time t2, we come and do another experiment on these three boxes by opening them and doing right interferences, etc., and we conclude that the state of the electron at time t2 was equal to box number 1 plus box number 2 minus box number 3. We can find this state because it's not orthogonal to this one. In fact, the scalar product of this state and that state is equal to 1. So we know that there is a probability of 1/3 to find this state. And we ask now, how can we do experiments in the middle time that will check what's happening in this box? And we find something really exciting when we do only weak measurements. How can we do a weak measurement to find if the electron is here or not? So the obvious thing, where is the eraser? Here. So we have this box here, and we want to find what is inside this box without opening it. Because if we open it, it's a strong experiment that will destroy what we are trying to see. So we are not allowed to open the box to see what is inside. But instead, what we can do all kinds of tests outside the box that will tell us what is inside. And the test that we can do outside the box is, for example, we can measure at different location the electric field. Or we can measure different location the magnetic field. Or we can measure at different location the gravitational field. Each one of these measurements will be a weak measurement. How do we know that if we make a strong experiment of the electric field here, it will still be a weak measurement as far as the electron inside is concerned? Because when we measure a strong experiment of the electric field, we see not only the electric field produced by the electron, but also the electric field that would be there in the vacuum when we do a measurement. We know that in the vacuum, when we do a measurement of the electric field, we don't find zero, we find an uncertain electric field, and only in the average of many experiments we find the average zero, but there is a minimum electric field, just like when we consider, for example, the ground state of an harmonic oscillator. In classical physics, then we know that the energy of that oscillator will be zero, the momentum and position will be zero. But in quantum mechanics, when we have an oscillator and we measure the ground state, position, momentum, and energy, we can't find zero because of the uncertainty relation. Delta X, delta P is different from zero, so we can't have the position and the momentum equal to zero. And in fact, we find that the minimum energy is 1/2 h bar omega. So that is true also about the vacuum. The vacuum is really for electromagnetic field is a collection of harmonic oscillators, and each one of them has a minimum energy of 1/2 bar h omega for that mode. And all of this collection tells us that if we make a measurement of the electric field here, it's like making a measurement of the position of a harmonic oscillator in the ground state, we see a large uncertainty here. That uncertainty is much bigger than the electric field produced by the electron here. How do we know that? This is a very important statement. We know that if we do an experiment in the laboratory, we can set an electron that goes one orbit or goes another orbit, and we see interference pattern here if we repeat the experiment on many electrons. Now, if the electric field produced here by the electron could be observed, then we could have told if the electron went this way or went this way, because the electric field here would be different. Only if the difference between the two electric fields is much smaller than the uncertainty in the vacuum here, only then we can see the interference pattern. Otherwise, the measurement of the electric field here will tell us whether the electron went this way or that way, and then we will destroy the interference. So we know, therefore, that if we come and measure outside of this box the electric field, we make a strong measurement of the electric field in any of these locations, a strong measurement. But the answer that we get does not tell us yet in the individual case what was inside here, because in one case, when we do this experiment, it will give us no information at all, because the electric field that we measure could have come due to the vacuum and not to the electron there. You have a question?
I think the point is that when the electron comes here, then there is no record of this electric field in this field. When the electron, during the experiment, there is electric field which you can distinguish.
No, that doesn't help you, because, no, you're wrong. Look, suppose we start the electron in this linear superposition, and it goes like that, and then shows interference here. We can do an experiment here that will tell us where the electron was in the past, and we disturb the electron only in the future after the experiment was over.
This is what I say, that the electric field far away, when it will come here, will not be different from the vacuum far away. But during the process, near, very close to electron, of course, the electric field will be bigger than the electric field of the vacuum. It's just...
Look, I'm just telling you that if suppose the electron live for a long time along here, and only then we combine it to make the interference. If, in this case, if the measurement outside will tell us whether it was here or here, that will destroy the interference.
If you make a measurement.
Yes, I measure the electric field.
If you don't make a measurement...
Okay, but I'm telling you, we should do the calculation, and actually you can also do an experiment in the laboratory. Maybe it was not done, but what quantum mechanics predicts, that if you do this strong experiment here, during this short time that the electron is moving here, that experiment will never tell you whether the electron is here and here. This you can do by calculation, and you can check it in the laboratory. Believe me that this is the case.
Yakir, question. Is this related to alpha being small in some way?
Sorry, who is talking?
Me.
Yes.
Is this in any way related to the smallness of the coupling, alpha being one?
To what?
The smallness of alpha electromagnetic is usually, the effect of charges is small. Alpha is being one.
Yeah, it's related to the fact whether the electron, if the electron moving, if I do the following thing, I accelerate the electron, and then I let it go like this, and then I combine it again. When I accelerate it here, there is a probability to emit a photon, right? If that photon has short enough wavelength that will be shorter than that distance, a photon will carry information whether the electron was here or here. And the answer is the probability is very small for this to happen. That's another way to understand why this experiment that I'm talking about does not tell us where the electron is. Thank you. So, we come to our mysterious box, and we do strong experiment of the electric field here. We do strong experiment of the magnetic field, of the gravitational field here, and this tells us practically nothing on what is here in individual case. Then we repeat this experiment again and again and again, each time preparing the three boxes, doing the experiment in the middle time, and then checking the final boundary condition. And we made strong experiments of the electric, magnetic, and gravitational field in each time. And we wrote down the results for experiment number 1, experiment number 2, etc. Out of this list of results, we collect only those results that corresponded to the cases where we were successful in getting the final boundary condition. And lo and behold, when we collect only those results and we made enough experiments, then, although in each individual case we found very little information, but if we repeat this experiment many, many times, the vacuum fluctuation grows a square root of n, because it's like a noise. Sometimes it's positive, sometimes it's negative. But in our results, we got each time, for these cases, the same result. So eventually, if we do the experiment on sufficiently number of particles and collect only the experiments that were successful, lo and behold, we'll find that the electric field here, for all these boxes together, told us that in each case, there was here a particle with the opposite charge. Similarly, it will tell us that in each individual case, there was a particle here with a negative mass. We couldn't find it in a single experiment, but if we collect the result of the whole experiment, even though for each one we checked it very, very weakly, nevertheless, the combined result tells us that indeed the only explanation for this combined result is that each individual case there was here a particle with the opposite properties. So this is a very, very interesting new kind of reality. And I want to add that we were told all the time that in quantum mechanics, because of the uncertainty principle, we cannot speak about the reality of a quantum system, because what we measure is always not only the property of the system, but also the uncertain disturbance that we make to the system. This weak measurement gives us a new way to think about quantum reality, because we see now that it's possible to speak about a quantum reality and check it without disturbing it. So the weak measurements are extremely important because they give us a new tool to think about what happens in the quantum domain without disturbing it. And that is going to be the way to resolve the mystery of the two-slit experiment. And let me show you how this goes. So what is the mystery of the two-slit experiment that Feynman and anyone that thinks seriously about quantum mechanics, not just how to solve what's happening, but really to think what is going on there, you find a big mystery. The big mystery is the following. We have a screen with two slits. We send one after the other individual particles, say electron. It comes in as a plane wave, a single electron. It goes through this slit like that. It goes through this slit like that. And if we put here a photographic plate, say, we find that in the region where there is overlap, in this region where there is overlap between the contribution that came from here and the contribution that came from here, we see interference pattern. We see location, for example, where no electron will appear there. We send one electron after electron, huge number of electrons, and we see that none of them appeared in a location where there is destructive interference. On the other hand, if either of the slits were open and the other closed, we always will get some electrons there. So the usual way to think about it was to say the only way to understand it, is to say that in some way the electron must have gone through both slits at the same time. That's why people, when they speak about quantum mechanics, tells you that a quantum particle can be at the same time at two different locations. But then you ask yourself, what does it mean that a particle is at the same time at two different locations? You tell this to the man in the street, and he asks you, hey, you're telling me the electron at the same time it can be at two different locations? The electron has a charge, E, and a mass, M. What happened to this charge and mass? Is it split, half of it in one place and half of it in the other place? No, you tell him, no, it's not that. So what is there in the two places? You tell him this is something that we call amplitude, and you will never be able to understand it, what it means to be an amplitude, to be in two different locations. But really, to think about it, forget about mathematics. What does it mean to say that an electron is at the same time in two different locations? If we say that the charge and the mass are in one location, so what is in the other location? Something empty amplitude? Or you have to say that there is something that we really don't understand. And indeed, if we do check the electron around here, we always find it in one location. So this mysterious wave that suppose there can never be seen directly. It's only something that we infer indirectly, because there is no other way that we can understand it. Now I propose a new way to understand it. And the new way goes like this. We send one electron here. Instead of putting a photographic plate here, we do a weak measurement to measure weakly the projection operators on different locations here. And we do this so weakly that we don't disturb at all the state of the electron. So after we do this weak measurement on the single electron, we can still say that we didn't disturb the state of the electron, so we know that the state that came from this slit and the state that came from this slit are orthogonal to each other. So in principle, not in practice, but in principle, we can do an experiment later that will tell us whether the electron came from here or the electron came from there, because we did not disturb it. If we did not disturb it, then we continue this experiment many times. On each individual case, we get very little information from our weak measurement, but in each case we knew exactly whether the electron came from this slit or the electron came from that slit. And we collect all these weak measurements, and we find, lo and behold, that the projection operator where the destructive interference happened, indeed, the weak measurement of that projection operator when we collect all the information, get us 0. So we see the interference pattern, and we see nevertheless through which slit each particle went. This is extremely important. That means that the conclusion that we made up to now, that the only way to explain interference is by saying that the particle to show the interference pattern by weak measurement without disturbing the information through which the particle went. We can find this information later, not in the beginning, because in the beginning, if we knew through which the particle went, there would be no interference. So we are now making a combination of pre and post selection and weak measurement in the middle that give us completely new insight into this double-slit experiment. Yes?
I'm getting so excited about this, Yakir.
Sorry?
I'm getting so excited about this.
Yeah?
I'd love you to resolve a question that's in my mind.
Yeah.
And that is this, that at one point you said, having made the weak measurement, we nevertheless know exactly which, from the subsequent measurement over to the right of the board.
The final measurement tells us which the particle
We
went.
know exactly which slit it went through.
Yeah.
So my question is whether we know probably which slit it came through, but not necessarily exactly.
Yeah, but yeah.
Whether
The whole point of weak measurements is the following. You know that in classical physics, we consider the idea of a test particle. We want to see if a given charge is here. We wanted to find out by measurement of the electric field here whether the particle was here, but we wanted this measurement not to disturb the particle. So what we used in classical physics, the idea that we take a test particle that has such a small charge that it will disturb at all the particle here, and we get therefore a very small effect on the test charge, but we can classically observe it, and that will be a way to measure the location of this charge without disturbing it. So
I follow all that.
let me finish. Now we come in quantum mechanics. In quantum mechanics, we cannot have a test charge because of the large uncertainty in momentum and charge. So nevertheless, we say, in this individual experiment, we are going to measure here by a measuring device that has a large uncertainty in its pointer, the same thing as the vacuum uncertainty in the electric field, so forget about the vacuum uncertainty. Instead, I have a measuring device that has a large uncertainty in the pointer. It makes a very weak measurement here, and it disturbs very little the particle here, but we see very little information. Then we collect many, many, many results. And when we collect all of these results, we see that the effect of all of them was to collect all the sum of the charges there, but multiplied by a very small coupling strength. So although we got only a finite result here, collecting all of them, we say that that final result can have happened only if in all of these cases the charge was here, because we measured the total charge multiplied by a very small number. The fact that we multiplied by a very small number that tells us that we can't tell in the individual case how much was there. Nevertheless, when we collect all of them, multiplied by this small number, we say the total charge there, in all the boxes together, was the shift of the pointer multiplied by a very small number. We divide by this small number, and we find that indeed the total charge here was n. So although in each individual case the weak measurement tells us very little, when we collect all the results, it tells us information of each one of them up to a very small fraction of square root of n. That is the beauty of the weak measurement. Although, yeah.
I follow all that.
Yeah.
And so now let me come to my question or restate my question. And there must be a quantitative answer to this.
Yeah.
That that whether the very small uncertainty in the final result, as a result of the series of weak measurements, balances the very small amount of information that you got from the cumulative weak measurements.
Yeah, that's what I was trying to explain. So the idea is, I get from the weak measurement in each individual case absolutely no information at all at the limit of when the weakness goes to zero. But I collect infinite number of such experiments, a huge number of such experiments. Then I collect the results of all the shifting, very small shifting in all the measuring device. I collect the sum of all these small shifts. It will be a finite thing. I divide that finite shift by the total number of particles, and then I find that if I take the total shift, this was the total charge here divided by n. So I have a finite shift here for an infinite number of particles. I take this finite shift and multiply by n. That will tell me exactly what was here in each individual case, up to some small uncertainty.
Well,
No, it really works.
So now I'm seeing a tension between exactly and a very small uncertainty. And there must be a quantitative argument.
Yeah, there is a quantitative argument which goes the following. If the number of particles, number of experiments that I have is n, the minimum interaction length must be lambda divided by square root of n, where lambda is larger than 1. Then when I do n experiments, I will get a shift which will be lambda times the total uncertainty of the measuring device. If lambda is larger than 1, I will be able to see it. It's a quantitative statement, and when the number of experiments go to infinite, indeed the disturbance goes to 0, because I can do each experiment to the accuracy interaction of lambda with square root of n. And so this is a quantitative statement that I can discuss with you
We have
privately.
a very strict rule in our laboratory. that
Sorry?
We have a strict rule in our laboratory that
Yeah.
0 and infinity are useful mathematical tools, but nothing in the laboratory is ever either 0 or infinity.
No, but look, now there were many experiments done in many laboratories measuring these weak values and seeing that it really works, because the way that was done in the laboratories were to take a very large number of photons, collecting in the experiment only a very small fraction of them, and then you could see this weak value amplification, so it can be done in the laboratory.
Just the weak value measurements. I'm worried about the very small, but not 0, uncertainty in the strong measurement at the end of
Oh, no, that you can very easily show that if you do a weak measurement here, the disturbance, suppose I start with a particle that came only from here. I do this weak measurement on this single particle. Then I check what is the probability to see later this particle coming from here, or a mistake to see the particle coming from there. And you can show that if the strength of the coupling goes to 0 with lambda over square root of n, the number of mistakes you will do will be of the order of lambda square over n. So n is large in the overwhelming number of cases, even though you did the weak measurement in the middle, you check later where the particle went, you see the probability of finding a wrong answer goes to 0 is lambda square over n. And so you can calculate it exactly.
Maybe that's the answer I was looking for.
Okay, any other question? Yes.
Yes, so my question is, if you make a weak measurements of the position projected, and then
Yeah.
strong measurement also of the position, I don't understand how you can get information on the slit, because where you make a weak measurement, you have waves coming from both slits. If you close one slit, you will get a different weak value than if you have both slits open. So how can you infer where which slit the particle came from?
Oh, because I'm saying if you have a screen and you close this slit and you send a plane wave, you know that the particle will come out in this state. Now, this is a well-defined state. In principle, you can make a measurement here, not very practical measurement, but in principle, this can be a measurement here that tells you that this was the state, right? Because if the particle went from here, if this was closed, and the particle went from here, you have a different state, this new state, a new state. And you can do an experiment here that will check that it was this state. So if both slits are open, and the particle came in a plane wave, you can do an experiment here to check whether it came from here and here. That will be an experiment, a strong experiment, that will tell me whether the particle came from here and here. This is like a post-selection that goes backwards and tells me where did the particle come from. Okay? So as long as I don't disturb the state, I can always do in the future an experiment that will tell me whether the particle came from this state or the particle came from this state, because these are two orthogonal states. In principle, there is always a way to distinguish between two orthogonal states. Now, if I do in the middle here a weak measurement on each electron, then of course this could disturb it. But at the limit, when I do huge number of experiments and I have a very, very weak coupling to the electron for each individual experiment, then I can show that if I close this slit and I do this weak measurement here on each electron, then I check. And I can see that in the overwhelming number of cases, the electron still will have here the wave function that propagates from here. That is the beauty of weak measurement. Any other questions? This is the most important.
Yeah.
Yeah.
Just
Yeah, okay.
I just want to make sure I'm understanding what's going
When you
on.
say you want to make sure you understand it, it's another way to say I don't believe it.
No,
Okay.
not true. I really just
All
want
right.
to make sure.
Yeah.
Most of the time you're right, but I just want to make sure.
Yeah.
In this case, the post-selection is really not playing any role, or not playing any role in making the weak measurement.
No, it does not play any role.
And
Right.
all it's doing,
It's
the
telling me-
later measurement is just a way of knowing which slit
Yeah.
it went through.
Yeah, because when I have here an ensemble of particles,
Right.
you know, this is very important. When you have an ensemble of particles, all of them in the same state,
Right.
the weak measurement in the middle can depend, if you collect the whole ensemble, on which experiment you are deciding to do later. Otherwise, it will be violation of the
So the weak
causality.
measurement would come out the way it does whether we did a later measurement or not.
That's right,
Right.
indeed.
So,
Yes.
so this weak measurement is what I don't call deterministic weak value.
So, say it again?
These weak values are expectation values, which the outcomes of
No, the answer,
expectation
no, they're not. They're not statistical. Look, this is a very important point. If I have just a single system, psi, and I apply some observable A to psi, I can write it as A1 times psi plus A2 times some orthogonal state to psi. Right? Now, what is A1 and A2? You can easily calculate it, that A1 is equal to the average of A in that state, and A2 is equal to the uncertainty of A in this individual state. This is true for individual particles. Therefore, in each individual particle, if I do a weak experiment, I find the weak value not as an average, but as a property of this mathematical statement. It's not a statement about many particles, it's a statement about the property of each individual particle, that when you make a weak measurement, the probability of producing a state here grows as epsilon square, and to the order of epsilon, you find this value for each individual particle. It has nothing to do with statistics.
Yakir,
Yeah.
there is, you send two, you open your two slits. Then you put some measuring device, which is a quantum thing which interacts with your particle.
Yeah, very briefly.
Yes, and the my claim that after this interaction, there is no, your measuring device will be in a mixed state. It will not be in a pure
No,
state.
immediately after the interaction, I make a strong measurement. My measuring device is a pointer.
Yes.
The pointer moved very little. I then make a strong experiment immediately on the pointer, measuring its momentum. There is no entanglement anymore.
But this is clearly your strong measurement of momentum will be probabilistic outcome.
Sorry?
It will not be deterministic outcome of momentum. You will have to make many of them, and then you'll have to make statistics.
Of course.
Yes. So what I will kind of say is a deterministic weak value is when your measuring device in a pure quantum state for which I know with certainty what will be the outcome if this is a weak value. So this, in my
Look, you are
language-
now talking about terminology. I'm talking about experimental fact. Do you object to my experimental fact is the following. Listen carefully. I am saying I describe to you an experiment. The experiment is you send one electron after the other in a plane wave. Each electron, you do a weak measurement on, say, a projection operator around the place where you're supposed to get negative interference. Wait till the end. I then, for each experiment, after I made this weak measurement, I check whether the electron came from this slit or from that slit, on each individual case. And I find that when the two slits are opened, when I collect all the results, I find that the weak value of the projection operator here was equal to 0, and therefore the strong value of it was equal to 0. And nevertheless, I can still tell on each of the electrons where it came from this slit or from that slit. That is my experimental fact. And I don't want to use now any terminology to say that I made here a deterministic experiment for weak value or not. I don't want to talk about that. I want to talk about experimental facts. That's all. Yes?
Well, now I have something of a dilemma because I was going to say there's just one thing I don't understand. That when Simon Saunders in Oxford says that, he means I completely disagree with everything you've been saying. And if I were to say that, I would risk being told to listen very carefully. So I'm
Yeah.
going to listen very carefully. The electron goes through the screen somehow and is subject to a weak measurement, which may be very weak,
Yeah.
but it gives a probability P, which may be very small.
Sorry?
The weak measurement gives
Yeah.
a probability P, which may be very small,
Right.
of then giving a false result with the subsequent strong measurement as to which slit the electron had gone through.
Fine.
Now, if I make a very large, but not infinite number of measurements, let's call it n, these measurements are not correlated.
The false.
So the number of
Yeah.
false results that I get does not go up as the square root of n, it goes linearly as n.
Sorry?
The number of false measurements that I'll get, the number of incorrect measurements, will not scale as the square root of n.
No, in this case there are no. The post-selection, since I made a very small disturbance on an ensemble, whenever an ensemble that all of them are in the same state, then I don't need to do a post-selection. It's enough just to do a weak measurement on the ensemble and get the property of the wave function of that ensemble without any post-selection.
There's no post-selection, but there is a final measurement as to which slit the...
Yeah, that final measurement, look, this is a very important point. Let me explain it carefully. if I have an ensemble of particles, all of them start with the same state psi. In the position representation, all of them have the same wave function psi of x. All of them. Then I come at a given time and measure the projection operator on psi of this psi. It will be psi sub psi. The weak value will be proportional to psi sub psi for each one of them. That statement for the whole ensemble cannot depend on which post selection I'm going to do, which measurement I am going to do in the future. Cannot, if I collect all the results in the future, that cannot affect which result I got in the middle. Otherwise, it will be a violation of causality. So if I do experiment on an ensemble of particles, and I do weak measurement on this ensemble, then the result for the whole ensemble of the collection of weak values has nothing to do, cannot depend on which experiment later I'm going to decide in order to get different post selection. For the whole ensemble, there is no effect. If I then post select only sub-ensembles, then of course that will depend on which measurement I made at the end. But the beauty of all this discussion is that I don't violate causality, even though I say that for sub-ensemble there is the weak value depends on what experiment I do at the end. But if I collect the result for all the ensemble, then it doesn't depend on which measurement I'm going to do in the future. This is very important.
That's fine.
Yeah?
What I think I'm feeling is that the measurements I do in the future will give me a false result with a probability of p per measurement.
1 over n.
No, not 1 over n. A probability of p.
Which is
Yeah, but I'm saying that whatever you decide to do later, I can decide to do later an experiment that will tell me that indeed the particle went through both slits. Or I can decide to do another experiment that for half of them it will tell me that it went through one, for the other through the other. But in the middle I collect all the results of the weak measurement independent of what post-selection result I got. Then it will always be the same thing. It doesn't depend on which post-selection I'm going to do.
I understand all that, but this only becomes significant if I do make the subsequent experiment.
Sorry?
All of this becomes significant only if I do make the subsequent experiments, because otherwise it's just a standard Young's double-slit experiment.
Yeah, so
So it only gains extra significance when I make a later experiment to try to determine.
it's significant for our interpretation, but not for the result in the middle.
Exactly.
The result in the middle will always be interference pattern, which I can check either by strong experiment or by weak measurement. And that result is independent of what experiment I'm going to do later. I'm now using the idea that because I did make of the ensemble only weak measurement, I can later come for each individual electron and find out through which slit it went with a very small mistake.
Exactly. And what I'm saying is, if I don't make the subsequent experiment, I haven't advanced the physics. I've just done a double-slit experiment and found an interference pattern. If I'm now trying to advance the physics by subsequently knowing through which slit I think
Yeah,
the electron had gone,
yes,
if the weak measurement has a probability of p of so deflecting the electron that I get an incorrect assessment of the slit through which the electron had gone, if the measurements are very, very weak, p is very, very small, but then I need to make a large number of measurements.
yeah, but I'm saying,
And wait a minute.
I've just told you that I have a proof that this weak information that comes from each electron cannot depend on which experiment I'm going to do in the future. Cannot depend. Therefore, if I conclude, suppose I made the weak measurement in the middle, and then I check that the electron at the end has the same initial state at the beginning. Namely, it went through the two slits according to usual interpretation. I do this measurement, I find that I'm always successful to find that the electron was not disturbed, and nevertheless in the middle I saw the interference pattern. I can instead decide to make at the end an experiment on each electron that told me through which slit it went. Again, if I collect the information of all the ensemble, not the sub-ensembles, I will get exactly the same answer. So for the whole ensemble, the answer of which measurement cannot depend which later experiment I decide to do in the electron.
So let me focus in on the question. I'm not asking for retrocausality, but I am questioning the statement that the final measurement tells me through which slit the electron went.
Yeah.
Because there will be an uncertainty in that.
No, but uncertainty goes to zero when the strength of the coupling to the weak measurement goes to zero. I can check it,
Yeah,
because let me say, if I...
Sorry, Yakir, let me just focus on the question. We don't allow zeros in the laboratory. So the weak measurement, the disturbance cannot go to zero.
No, it can go to zero when n goes to infinite.
So maybe the misunderstanding is the difference between 1 over square root of n and 1 over n.
Exactly so.
And
That's it.
And it's exactly the case, because there are two different ways to approaching it, that it is okay. Because he tells you that it goes like lambda.
Now I go to the limit. I first decide how much disturbance I want to have, and then that tells me what number of particles, minimum number of particles, I have to repeat the experiment in order to see something. So if I decide that I want to have the weak measurement to have a disturbance that goes to zero as square root of n, as 1 over square root of n, I then decide that I must do the experiment n times more, to repeat the experiment n times before I can begin something. So you tell me first of all how much you want to disturb the information through which slit the particle went, then I will tell you how to do the experiment, nevertheless to see the interference pattern by increasing the number of particles that I do the experiment on.
I think Jeff's going to bring
What's
it to a
that?
close.
No, I wouldn't cut this off. However,
Maybe at the end of the thing we can have another session of questions to
how
me.
do people feel about that? Do you want to? So, we have an option here. I don't know what, there is a beach calling, or, so there was a possibility we could end before lunch, then have lunch, then beach, or we could do according to the schedule.
We can have another hour discussion, then go to the beach. Whatever, it's your fault.
Some people.
Okay, thank you.
Our president will miss it, but what is the, do you have any opinion here?
Maybe 1 hour for lunch and 1 hour for this. And speak
Sure, you should.
Are you asking this group if they have an opinion?
Okay, I want to end my talk by saying that I enjoyed this conference immensely. I want again to thank the people that organized it, Jeff, Andrew, Daniele. Thank you very much. And also, I don't know if Sarah is here, also Sarah was the secretary. And I want to thank everybody that came to help me to celebrate my 91 minus epsilon birthday. Thank you very much.